This is mathematics tutorial by Ajela on a course called Linear Algebra 2. My name is Ajela Hailo. As you remember, you can find this video on mathematics tutorial Amharic on YouTube. So the first question is, as you see, this is question number 1. Label the following statements by saying true or false. Let's highlight the first. All the question, it says the first, as you see, every linear operator on n-dimensional vector space has n distinct eigenvalues. What do you guess on this? Is it true or false? That is the question. The next, if a real matrix has one eigenvectors, then it has an infinite numbers of eigenvectors. What do you suggest for this? Similarly, just read this is video, so you can pause and read these statements. So let's see each questions one by one. As you see, every linear operator on an n-dimensional vector space has n distinct eigenvalues. You see, this is false. It's false because, for example, an identity map I2, that means I2 identity map has two eigenvalues, 1, 1. Identity, take simply identity matrix, or you can say 3 identity matrix, 3 by 3 identity matrix. In that case, the eigenvalues are 1, 1, 1. So every linear operator on n-dimensional vector space has n distinct eigenvalue. False. It may have only one distinct. It may have maybe 2, maybe n's, but every is not. So this is false statement. The second, B, if a real matrix has one eigenvector, then it has an infinite numbers of eigenvalue. As by the definition, eigenvector means the non-zero scalar. Just take a field from a field scalar, then the eigenvector times the scalar multiple will be repeated eigenvector, just eigenspace, the one which we create an eigenspace. So there is infinite, so the statement is true. In the case of C, from the previous question, C, there exists a square matrix with no eigenvectors. Does such matrix exist? Yes. For example, take a 2 by 2 matrix with diagonal 3, 0, 0, and the then diagonal 3, 1, minus 1. In this case, so in this case, for this matrix, you will see the summary of the matrix at the end of after K. So in that case, you will get the statement for the answer for this question is yes, no eigenvector. No eigenvector. Sometimes we may don't have, or the existence maybe no. Okay, let's proceed to D. Eigenvalue must have non-zero scalars. Eigenvalue can be 0, no problem. Eigenvector non-zero by the definition, but eigenvalue may be 0, scalar 0 from the field. E, any two eigenvectors are linearly independent. Any two eigenvectors linearly independent. Any two eigenvectors linearly independent, but there is a possibility sometimes they may be linearly dependent. So the answer is again no. Okay, in this case, F, as you see, the sum of two eigenvalues of a linear operator T is also an eigenvalues of T. Is that possible? The sum of two eigenvalue? No. This is false statement, because sometimes the linear operator T may have only two eigenvalues, but when we add the two eigenvalues, we get the third different numbers. But that's the third different number is not the eigenvalue of the first for the linear operator T. Similarly, for the matrix, it is also false for the matrix. Okay, G, a linear operator on an infinite dimensional vector space never have eigenvalues. Never have eigenvalues. No. For example, let P be the space of all polynomial. So just take P. Then the linear operator T from P to P. Consider this one. Thus, we know that 1 in the case of polynomial. 1 is an eigenvalue. Just if polynomial of degree 2, 1, it will continue, but this is not. There is possible. I'll give you the specific example at the end of this video. Okay, an n by n matrix A with entries from a field F is similar to diagonal matrix if and only if there is a basis f the powers of n consisting of eigenvectors of A. So for this question, just think the definition. The answer is yes. The answer is yes. You can take the polynomial P, then the base polynomial, just you can take identity matrix, as I will explain this one. But now when you see this 8, as you see the question, the answer is yes, or it means true. That matrix A is similar to the diagonal matrix D, means that there is some invertible matrix P which satisfies this equation by the definition. Since P is invertible, so P is written like this for some base beta alpha, where beta is standard base for the field. So the first statement is equivalent to A. A is diagonalizable, that is A is diagonalizable, and the desired result comes through by the theorem in the course. So just you can check this one for C, for Z, for up to I's. Let's continue I. Question number 1. Similar matrix always have the same eigenvalues. Is that possible? Yes. Similar matrix have the same characteristics polynomial, and the solution of the characteristics polynomial is equal to 0 is the same, so that implies they will have the same eigenvalues. What about J? J, just read the question. The answer is no. The similar matrix always have the same eigenvectors. In the case of vectors, false. In this case, eigenvalue. In this case, eigenvectors, false. And the case, the sum of two eigenvectors of an operator T is always an eigenvector. What do you suggest on this? Is it true or false? Think the definition. The statement is false. The constant multiple of the eigenvector is eigenvector, but the sum of two eigenvector is not an eigenvector for the matrix. Then next we'll proceed to question number 2. But before that, these are the solution for J and the K. That means with a specific example, you can take this matrix, you can take this matrix in the case of J. Thanks for listening and watching this video. I will prepare the better attractive video in the next time. This is an introduction part, so I think you'll subscribe and suggest me for the next video. Thanks for listening.